Hey guys, I'm looking at example 3 on page 340 in your textbook from section 6.4. I want us to go through this example carefully, even though the solution is in your textbook, because there's a lot of new terminology and stuff that I want to make sure you guys really understand. So first of all, you should just stop this video for a minute and review the definitions at the top of page 340 of heading, ground velocity, and air velocity that apply to this question, because I'm going to refer to them as I go. So I've written my, the question says an airplane is flying at an airspeed of 500 kilometers per hour on a heading of 40 degrees. A 150 kilometer wind is blowing from a bearing of 120 degrees. Determine the ground velocity of the airplane and the direction of flight. So the airspeed of the plane is actually the speed of the plane relative to still air. So assuming that there is no wind, it is the speed that the plane is set to fly. And it says on a heading of 40 degrees, which basically means at a true bearing of 40 degrees. So I've written that down as my given. Notice that the notation I'm using for the plane, the airspeed is the velocity of the plane relative to the air. And that's why I have PVA. Plane relative to the air, velocity of the plane relative to the air. For the wind, that's actually the velocity of the air relative to the ground, how fast the air is moving relative to the ground, so I've called that AVG, and that's given as 150 kilometers per hour from a bearing of 120 degrees. Now, I really want you to pay close attention to this from a bearing business, because that is a little bit tricky and causes a lot of issues usually with doing proper solutions for this type of question. So I'm going to show you that in detail in a minute on my vector diagram below. We're asked to find the ground velocity of the airplane, and I'm calling that PVG for the plane's velocity relative to the ground. Now, the most important thing in this problem that allows us to solve it is that the plane's velocity relative to the ground is actually the vector addition of the plane's velocity relative to the air and the air's velocity relative to the ground. And this is part of the reason why I chose this notation, because it makes sense that you end up with, we have PVA plus AVG, you end up with PVG. Alright, so on my vector diagram below, I already have drawn and labeled my plane's velocity relative to the air, which is at a bearing of 40 degrees, so that's 40 degrees from 0 turning clockwise. And I've put on my velocity of the wind, AVG, but I have not yet put an arrowhead on it, because since it's from a bearing of 120 degrees, normally at a bearing of 120 degrees I would put my arrowhead over here. But from a bearing of 120 degrees is actually the exact opposite of that. So I need to put my arrowhead on the opposite end of that vector, which in this case is pointing directly at the origin. So this is my AVG, velocity of the wind or air relative to the ground. What I want to find, what I'm asked to find, is my resultant PVG, plane's velocity relative to the ground, which will go from the tail. Now notice my vectors are tip to tail, right? AVG is tip to tail with PVA. Does not matter that AVG comes first, because vector addition is commutative, right? As you learned in the section on vector addition. So it does not matter that AVG comes first and PVA comes second in this case, in the tip to tail positioning. My resultant is still from the tail of one to the tip of the next, assuming they are tip to tail, which they are. So this is my PVG, the resultant that I'm trying to find. So let me go back here. So we need to figure out how we're going to find the magnitude and direction of that resultant vector. In order to find the magnitude, I know the magnitude of PVA. I know the magnitude of AVG. All I need to know is the angle between them, and I can use cosine law to find its magnitude. So I have an angle of 40 degrees to here, and then an angle of 120 from 0 all the way down to AVG. So if I just subtract them, I will get an angle of 80 degrees for the angle inside the triangle there, between PVA and AVG. So therefore, I can use cosine law now to find the magnitude of PVG, which I'm going to go to the next page to do. So the magnitude of PVG, remember your magnitude, your absolute value signs around a vector mean magnitude, is going to be the magnitude of the 500 kilometers per hour for the plane's velocity relative to the air, plus the wind, 150 squared, minus 2 times 500 times 150 times the cosine of the angle between them, which we found to be 80 degrees. So once you do all your calculations, you can of course put this whole thing in your calculator in one step. Just do it exactly as it's written with brackets and all. Make sure that you square root it after you get the answer to that, and you will get something approximately equal to 496.44 kilometers per hour. So that's our magnitude of the plane's velocity relative to the ground. Now we need the direction of that vector. So that's a little bit trickier to find, but we can definitely do it. Let's put a compass rose at the tail end of that vector, because we always want the angle at the tail of the resultant, and we use that to name its direction. If we could get this angle right in here, then we could name it as a true bearing. But let's see what we can do, because it's a little bit complicated to figure out here. If I look over here at this angle here, I'm just going to put a green dot there because it's a little small to write in there. If I knew that angle, then I would also know this angle over here, because there's a Z pattern there, right? 1, 2, 3, Z pattern. Okay. Now I do know that angle there because I know that my wind velocity was at a bearing of 120 degrees, or at least the angle here was from a bearing of 120 degrees. And so the remaining angle here would be 180 minus 120, which is 60 degrees. Okay, now this is getting a little bit messed up, this diagram, so I'm just going to go to the next page and redraw it. So I have something that looks somewhat like this. I know that this is 80 degrees. I know that this is 60. Therefore, an angle in here is also 60. Okay? Now that's good because I can now use sine law to find this entire angle in this triangle, and then just subtract 60 from it, and I will have this angle here, which is what I want to name the direction of PVG as a true bearing. So this is PVA, and this one over here is AVG. Okay? All right. So let's call the angle that I want to find here in the triangle theta. Then in that case, the sine of theta over the side across from it, which was PVA, which we know had a magnitude of 500 kilometers per hour. So sine theta over 500 is equal to an angle that I know, which is 80 degrees, the sine of 80 degrees, over the side across from it, which I just found the magnitude to be 496.44. All right, so do your calculations and solve for theta there. Comes out to approximately 83 degrees. Okay, so that entire angle, theta, is 83 degrees. We know that the green angle that I drew over here is 60 degrees. Therefore, PVG has an approximate magnitude, let's just round that down to 496 kilometers per hour at a bearing of approximately 23 degrees because 83 degrees minus the 60 is 23 degrees. Now, I just want to go back a minute to my givens and point out, because I forgot to point it out before, that when you have angles at a bearing, they must be written with 3 digits. So if there aren't 3 digits in the actual number, then you add a 0 in front. So this 040 degrees tells you that it's a true bearing. And so that's why here in my final answer I did at, and I'm being lazy really, I should write at a true bearing of, but I'm just doing it as a short form at 023 degrees, because the 0 in front of the 23 tells me that it's a true bearing anyway.